Hi, everybody. My name is Ryan Fobel. I'm a PhD student at the University of Toronto, and I'm really excited to be here today to tell you about how we're using open source hardware to develop a low-cost, general-purpose laboratory automation platform. So for people who haven't heard of microfluidics, it's basically exactly what it sounds like. We're moving small volumes of liquid on small chips. And so we're all very familiar with the revolution that we've seen in the computing industry, where 60 years ago, these computers took up an entire room, and they're very expensive, and they were very limited in what they could do. And then if you fast forward to today, everybody in this room probably is walking around with a smartphone in their pocket, small, they're cheap, and they're everywhere. And so microfluidics really has the goal of doing the same thing in the biology and chemistry space. So taking these laboratories right now that take up entire rooms and shrinking them down into these tiny chips, making everything cheap and everywhere. So just one application of microfluidics is point-of-care diagnostics. So on this slide, you can see the iStat, which is sort of the market leader in commercial, sort of the state-of-the-art in commercial microfluidics right now. This is a small handheld device made by Abbott, point of care. And if you can imagine, you go into an emergency room with chest pains, you can basically put a couple of drops of blood into this machine, and within a couple of minutes, you get a result back. It scans a panel of cardiac markers, and will tell you if you're having a heart attack or if it's, a false alarm. And you can see on this list, there are a lot of advantages to miniaturization and automation of these types of tests. So it gets cheaper, it's more convenient for the patients, you can get your results very quickly, and it cuts down on operator error and labor costs. And there are lots of other applications for microfluidics in research and development, studying cells, doing chemical synthesis, and basically anything that you can do in a tube or a petri dish or a beaker, you can do with microfluidics. So we work in a sort of subfield of microfluidics called digital microfluidics. And in this platform, this chip is about the size of a credit card. And we're manipulating these tiny drops of liquid on an open platform of electrodes using electric fields. And really, the advantage to this particular technology is that you can use a very generic device, so this very generic array, and the functionality is actually just controlled by software. And all of the electronics are solid state, so you can make a very portable device that's low power. And really the only sort of downside is that the throughput is not quite as good as some other techniques. But you can kind of think of this as like being a computer, a CPU of microfluidics. So it's maybe not as fast as a GPU or integrated circuit, but it's very flexible and you can do all kinds of things. This is the instrument that our group has been working on. We released it actually at this conference 2 years ago. And at that time, the instrument cost about $5,000 to build. And since then, we've really been focusing on trying to build a community around this project and trying to further lower the barriers to entry. So trying to reduce the cost of the instrument and also to figure out cheaper and easier ways to fabricate the consumable chips. So 2 years later now, we've got 17 of these systems around the world, 7 in our lab, and 10 other labs around the world have built them, which we're really encouraged by because it's not a small thing. People are paying $5,000, and a lot of these people aren't engineers, and they're just really excited about the technology and have built these things. So we're really excited, and we think it's going to get bigger. And one of the things that really gives us a lot of optimism is this project, which was released a couple months ago. It's a kind of a derivative of our project, and it's called OpenDrop. It's made by some biohackers in Europe, and they're part of the Hackteria network, for people who are familiar with the DIY bio scene. They make a lot of cheap open source lab equipment. But the really cool thing about this chip is that it basically is a shield for an Arduino Uno, so it's very small and portable. It runs off 5 volts, and it costs about $100 to make. So this really makes it easy for people to get into this space and start playing around. And doesn't quite have all the features that we have in our lab system, but we can really adopt a lot of these cost-saving features and maybe hopefully get something that has those features, but is at a much lower price point. And we've written a plugin and firmware for this system that can be controlled with the same software that runs the DropBot. And so even if you can get these really cheap instruments, the biggest problem then becomes the devices. So in our academic labs, these devices are made with photolithography. And so this is an expensive process. It costs about $20 to $50 to make a single chip. Plus you need access to clean room facilities. So it's really hard. That's kind of going to be the bottleneck. And we've been working on taking some inspiration from the printed electronics industry, figuring out ways to print these chips using inkjet printers. And we've been able to do this. We can now print sheets of these devices in about 30 seconds on a standard office printer. So we're really excited about this technology and think, again, this is going to make this technology more easily adoptable by lots of people. And so all of these kind of advances that we've been seeing really, along with some other work in the lab, developing things on developing the diagnostic tests on the biology side, allowed us to get a couple of grants from Grand Challenges Canada and Center for Disease Control. And we're really excited about this project where we're going to be actually taking our instrument to Kenya and applying it in a refugee camp there. And in these camps, measles and rubella, although they're kind of eradicated in most of the developed world, they're still a big problem in places like this. So there's a real need for a test that you can do in the camp that's fast and cheap. And we're kind of nervous about taking our system out of the lab and into the field, but it's also a very exciting time for us. So look forward to that. And I just quickly want to plug a couple of other open hardware projects from our lab. This first one here is called the DStat. Sorry, the slide's kind of messed up there, but this is basically a really cheap and affordable potentiostat, which is used for doing electrochemical measurements, and also you can do really sensitive current measurements. And we use that actually in the instrument we're taking to Kenya. And you can operate this standalone, and it also integrates really well into our system. And then the other project that I think some people might be interested in is this Arduino RPC Python package that my brother Christian, who's also here, he's developed that. And it's actually really cool. You can write functions on your Arduino, and then basically the software will scan your Arduino file and generate all of the protocols and code for communication so that you can trigger those functions from your PC or from other Arduinos and get all these microcontrollers talking to each other. And we use this very extensively in our project and think it could be useful for other people too. So just a couple of final thoughts. Building open hardware is actually much harder than not doing it in the open. It's a lot of extra work, but in our experience, it really pays off, and it forces you to adopt good practices. So it sort of forces you to write documentation and make sure other people can actually reproduce your results. And I think if you're really interested in getting your work out there and having impact, then it makes a lot of sense for people to adopt this model. And I do think that open hardware has a lot of potential to really make science move faster, but there are some problems still with the way that academics are incentivized, and it's not easy to get funding and to publish tool development. And I think that's a big problem and something that we need to figure out ways to make that better. So with that, I just want to thank all these awesome projects that we use in our work, and we wouldn't be able to do it without them, and our funding, and several other people in the lab. And also my wife for letting me come to this conference. It's our anniversary today, so. But I'm so happy to be here. Thanks so much.